Hi everyone, my name is Andy Dolan. I'll be presenting our work on behalf of myself, Dr. Indrakshi and Dr. Suryadipta Majumdar. Our work is proactively extracting IoT device capabilities and application to smart homes. So let's jump right in. So I want to start with some practical motivations and motivating examples. Why do we want to extract device capabilities? And I frame this in two ways. On one hand, we have a trade-off for IoT vendors. Vendors want to market their product to consumers, but also make their product understandable in by providing the right amount of information to consumers. So they may inadvertently abstract away what a device is actually capable of doing. Now, on the other side, consumers have their own trade-off. We want to introduce devices into our homes that provide us with convenience and fun, but at the same time, we may be introducing privacy and security risks. The image on screen here is a Cloud Pets bear. This is a children's toy that includes a microphone so that you can pass messages back and forth through the actual bear. So what we may not see on the surface with this sort of innocuous, very cuddly looking figure is the fact that we're introducing a microphone into some potentially private environments. So another example for you, the Smart Mirror has been a very popular DIY project in the past couple years. Usually this is just a screen underneath a two-way or one-way mirror. This particular example was a take on using an AI model to do facial recognition and voice recognition, sort of a different spin on that. And so what this project actually does, again, sort of an innocuous face to it, of just a smart mirror, it also introduces both a camera and a microphone into those environments in which a microphone or a camera may not usually be present. Something like private areas like bathrooms and bedrooms where a mirror is often used. So I want to also touch on some awesome related work. This was a survey conducted that sort of reveals that we have these innate and natural intuitive security goals when it comes to IoT and device capabilities. So this work in particular put device capabilities in very plain terms, and you can see those on the left side. So the one that's circled now is live video. Doesn't matter which device, which vendor, the implementation. The point is that there's the capability of live video. This work in particular framed those capabilities in conjunction with device attributes like location within the operating environment or social relationships between those who are invoking these capabilities. And so this figure in particular is an example of those social relationships. And it always makes me chuckle because on the far left column we have the spouse, who is typically results in being allowed to invoke all of these actions at any time regardless of the situation. And then from the right column, we have the visiting family, who are more often than not allowed to invoke the same kinds of actions. So there are these innate security goals that we have in mind, especially when we put these capabilities in very plain terms. Another motivating example for you, we have the Google Nest Protect. This is a smoke detector and carbon monoxide detector. Very cool device because it offers the convenience and safety features of being able to push notifications directly to your phone if it detects carbon monoxide, smoke, or even steam, which may or may not be a problem in the kitchen. So one feature that's not entirely apparent when you're just looking at this device is the fact that it has a microphone. And we'll talk a little bit later on this, but it's also not directly clear in its vendor materials, which we'll talk about later as well, that the microphone is actually present on the device. And this is impactful both in the sense that in a single home where there's a single family unit, this can have impacts to privacy, but at the same time consider the multi-tenant environment, such as an apartment or a dorm room, where we have multiple either family units or individual tenants who could be impacted by the presence of a device like this. So why, I ask again, why do we want to enumerate device capabilities? Well, if we can understand what a device can do, we can try to constrain its behavior based around what it can do. And so part of what I mean by that is that we can provide more transparency to the user and security applications that act on behalf of the user. We can tell them what their device can actually do in very plain terms as a source of ground truth, and we can therefore enable them and empower them to make better informed security decisions. Additionally, it would be great to avoid interpreting device behavior through traffic analysis, anomaly detection, other techniques, which I'll talk a little bit more about in a couple slides. So, I just mentioned ground truth. How do we find ground truth? It's particularly difficult with IoT because devices are so heterogeneous and multifaceted, and this image is sort of analogous in that way, where we have many different functionalities bundled into any one device, and some of them can be potentially dangerous. So in order to secure something, we must understand what it does. We must understand what it's capable of doing. An additional goal is for us to learn proactively. We don't want to install a device in its operating environment and then find out about some potential capabilities that we don't actually want in the environment. So where can we find this information? Well, a good first step is to look at the instruction manual, to look at the vendor materials. The vendor provided specifications, documentation materials about a particular device, or in this case, a multi-tool. So this particular example gives us sort of an overview of some of the features that this pocket knife has. Now I'll bring this back to IoT. We have vendor materials of the same nature for lots of our devices. So we have technical specifications, we have marketing materials, and these different kind of pages that we'll talk a little bit more about later. So one thing that I want to touch on, and I'll go into detail in a few slides as well, is that these materials present a couple challenges, and those center around being interpreted automatically by some extraction system. And we'll talk a little bit more about that in a couple slides. So to present a broad overview, some of our research questions are as follows. How can IoT device capabilities be defined and represented generically across devices? We want to make sure that capabilities are in plain terms and that they're not dependent on the implementation of the hardware, the vendor of the hardware, or any of the device constraints. How can such IoT device capabilities be extracted automatically from vendor-provided documentation materials for devices from different vendors? Again, regardless of the vendor, regardless of the device, can we look at its vendor materials, its marketing pages, its technical specifications, and draw from those automatically in a streamlined fashion the capabilities that are associated with the device? So I want to touch on a couple different related works, which we sort of categorize into three primary categories. We have works that try to perform device fingerprinting. This is usually associating some unique identity with a device based on its behavior. This often involves network analysis of traffic on the wire, building profiles based on those behaviors, and being able to uniquely identify devices based on those interpreted behaviors. We also have application monitoring systems, which either perform code analysis or rely on event hooks or REST API calls and try to determine what a device is doing based on those pieces of information. Finally, we have access control systems in the context of IoT. And a few of these are permission-based systems to monitor individual IoT applications. So I want to talk about where our work fits in alongside those works. And our work is complementary to these because they can have their own benefits in interpreting device behavior based on some observable features of the device. Where our work comes in as a complementary work is that we address a couple key limitations. Notably, our solution is proactive. We don't need to install the device in order to understand what it can do. As long as we have the vendor specifications, we can provide some answers about what a device is capable of doing. Additionally, we don't require interpretation of device behaviors through things like network analysis or application source code. Again, it's proactive, so as long as we have access to the vendor materials, we can interpret and analyze those materials to enumerate device capabilities. So, in that vein, our core contributions are as follows. We introduce a new approach to proactively extract device capabilities using vendor-provided materials as ground truth to enable proactive verification of IoT security requirements. We provide a new concept of device capability in IoT, which can potentially be applied in future security solutions for various IoT applications. And we apply our approach in the context of the smart home using devices from various vendors. All right, so I'm going to jump into some more details on what we mean by vendor materials. These are specifications, marketing materials, any page that is about a device in question. So the obvious ones are those that are consumer facing, the ones that consumers look at when they're shopping for a device, the technical specifications, the marketing materials, the anecdotes, the reviews, things like this. We also have the less obvious candidates for vendor materials. We have things like firmware configurations, which are typically held statically within the firmware of the device itself. We have patents, and we have developer API documentations, things that are still accessible to us, but may not be as obvious as the consumer-facing vendor materials. Nonetheless, these kind of materials can provide a lot of information about the device and what it can do. So we have two notable assumptions about these materials. One, we can access them. So if a vendor doesn't release an instruction booklet or one isn't created, then it's not something that we can analyze. Our second assumption is that the vendor materials have a certain degree of completeness. And by that I mean, if, for example, a vendor uses a chipset that includes a certain sensor that they don't actually use, they may not include any details about that particular sensor in their documentation materials, and therefore we would not, our methodology would not include that sensor in our analysis. So what I mean to say is that the vendor materials are complete only to the degree to which they are complete. So back to that idea of the challenge of interpreting these materials. There's a lot going on when you look at any of these marketing pages, technical specification pages. Again, the goal is to provide an intuitive user experience that's able to market the product, make it easy to understand. In that way, we use lots of things like hierarchical layouts, nested tables, visual cues. So in this particular image, note the amounts of complexity that we have here. We have a top-level drop-down that indicates which category of device we're looking at, and then we have two separate columns that are mainly identified by their images. Now consider this from the perspective of a processing system that's meant to extract information that we get from this page intuitively as humans. So additionally, in that same way, there's no standard template for how to lay out these materials. There's no standard profile that all these materials must follow. And in that way, vendors strive to be different. They use unique templates, but they also use unique terminology. So you often see something like a phrase like smart sense technology, this obfuscation of capability, in the sense that they could be describing a certain set of sensors, but it takes some technical background information or knowledge to understand exactly what sensors or actuators they may be referring to. Another challenge, the materials are very brief. User engagement is a finite resource, and so vendors grapple with this as an optimization problem. They need to provide exactly the right amount of information to the user in order to market their product, make it understandable, but not overwhelm the user. Accordingly, the materials are often extremely brief. They're bulleted lists, they're individual anecdotes that come in the form of 2 sentences. They try to deliver this information as efficiently as possible. And when you have less words overall, the distribution is very unique. Most of the terms that occur most often are related to the primary functionality of the device. But recall that we want to try to understand all the functionalities of the device. And so one example that I have for you to show this is this word cloud that's on screen now. This word cloud was developed from the corpus of vendor materials from the Google Nest Cam Indoor, which we saw on the previous slide. Intuitively, you see that terms like camera, nest, and image appear fairly often. They're large in the word cloud. But I challenge you for the next 2 or 3 seconds to try to find the term microphone, which is as important to our purposes. And you'll note it's right there, and it's very small. Its frequency within that corpus is much smaller than that of other terms. Okay, breaking into our methodology for extracting device capabilities. This is an overview of our methodology, and I'll go through each of those pieces right now. So firstly, we've created a model for IoT devices, their transducers, and their capabilities. These are generics and types that we'll talk about in a couple slides. We have a pre-processing methodology that can extract from HTML and text sources textual content related to a device, whether it's from the technical specifications or the marketing materials. We also normalize that text in that we remove extraneous information, and we normalize the plurality, the case of the text that we get out of there. And then we do 2 things. We have a base of knowledge that we create from the vendor materials through a manual review process. Through this, we gain understanding about what terms are associated with devices, what transducers are commonly associated with certain device types, and once we have that ontology, we can use that as input along with the normalized text with an enumeration algorithm that I'll talk about in a couple slides as well, to produce an instance of that model where we can understand what capabilities are associated with which transducers, which are associated with the device in question. All right, so jumping into the capability model that we've developed for IoT. These are abstract relationships. Things are generics and types. They're not dependent on implementation and they're not dependent on vendor. So devices have transducers. We consider two kinds. We have sensors, which sense the environment, convert physical phenomena into data, and we have actuators, which take data and convert it into physical phenomena introduced to the environment. Transducers are innately associated with capabilities. What I mean by innately is that the primary functionality that comes with a transducer is an innate capability. So for example, image sensors are innately capable of light detection and image capture because that's their primary functionality. It's very natural and innate to them. In this way though, since we consider transducers as types as opposed to instances, some capabilities can be shared by different transducers. So this example is on screen here. A light sensor can detect light, so can an image sensor. So they share that abstract capability between them. Okay, so this raises the question, how do we go from a device, a particular device in fact, to its set of capabilities? Well, the capabilities of a device are just a sum of parts, and so a device can do what all of its transducers can do. So to find out what capabilities a particular device has, we first enumerate its transducers, and then we directly map from the transducers to the capabilities that are constituents of each transducer. So that's sort of a two-step hierarchy where we go from device to transducer set to associated capability set. All right, let's talk about building our base of knowledge, the ontology. So we do this through a manual review process where we literally go through these different vendor materials and take note of what inferences, what kind of intuitions we use to sort of understand what transducers and associated capabilities a device has. So for these examples, these are again from the Nest suite of materials, but if we have the Nest Cam indoor and its technical specifications, we might see these highlighted areas where we say, I see the term camera, I see the term image sensor, I see the term lens. That builds that understanding of this is probably talking about an image sensor and a camera, this kind of thing. We also build out what kinds of terminologies are associated with particular devices and transducers. And additionally, we also develop an understanding of which transducers are commonly associated to abstract device types. So in that sense, I mean, if we have the abstract device type of a camera, we understand that it commonly is associated with an image sensor, a microphone, and perhaps a speaker. Okay, on to our pre-processing methodology. So again, we assume that the vendor materials are being presented in HTML or a text format. We scrape them from the web. So one thing that's introduced in a web page is a lot of extraneous content. You have navigation links, headers, footers, copyright information. We've developed a methodology to eliminate those, and that's per vendor. So what I mean by that is that we use an HTML parser that can be parameterized by certain characteristics of the page, and specifically the contents of the page that we want, or the areas or blocks of the page that we want. What's convenient is that this often scales across different devices within the same vendor, because web design within a single vendor is often homogeneous. So in that way, if I specify that these particular HTML tags are indicative of the technical specification section for one device, that may be the same within the same vendor for a different device. So once we've extracted the textual content of the specific portion of the HTML that we want to extract, we normalize that text and homogenize it. What I mean by that is we normalize the case, we remove any terms that are not in the natural language processing model's dictionary, we remove any punctuation characters, and then we also use the natural language processing model's lemmatization to normalize its tense and its plurality to dictionary forms of each word. So for this example on screen, if the text that we extracted originally read, with the camera's array of motion sensors, video will be recorded automatically, that would be translated to camera array motion sensor, video record automatically. There's a normalization of the plurality, the possessive of camera, for example, and the case is all normalized. It makes it easier to process later. So just some results on the efficiency of our extraction and normalization techniques. We see that these both scale linearly. For the extraction of the HTML scales linearly with the size of the input materials. So the Nest suite of products have very large web pages. For each device, it's usually about 4 megabytes total between about 4 different vendor materials. When we run the HTML parser, which again is parameterized and it extracts out all of the script tags, all of the different extraneous information, it takes just a little under 20 seconds to extract all of that. On the normalization side, that also scales linearly with the number of lemmas that are extracted and normalized. Even when we're doing over 12,000 lemmas, and consider again that these materials are very brief, so there won't be that many lemmas oftentimes, we're still running at about half a second. So yeah, on to the methodology for extracting capabilities. So again, to remind you, the approach that we're going for here is to first enumerate the transducers that are associated with the device, and then we can directly map from the transducers to their static set of innate capabilities. One assumption that I want to share, we assume that nothing is known about the device beforehand, and again, once we have the transducers enumerated, we can map directly to the capabilities, and we use the ontology that we developed through the manual review process to perform that action. Okay, so quick side note, why not use existing text analytic techniques such as natural language processing or TF-IDF analysis? I want you to recall that vendor materials are not written like traditional text. They are not prose, they're not articles, they are very brief, they're an optimization problem, and so we have a situation where the distribution of terms, even the terms that are most relevant to transducers and therefore our purposes, only appear a handful of times. The figure on screen here is the same set of terms from the word cloud a good number of slides ago, and they're denoted here as which terms are relevant to our purposes versus irrelevant. And you can see that there's no clear pattern for how these are distributed. You can have terms like microphone, which only appear 7 times across the entire corpus. So, getting into our extraction technique, we look at the concept of a key term. This is one or more tokens, and we have 2 classes of them related to ambiguity. We have indicative terms, which are unambiguously indicative of the presence of a transducer when they're found in the text. So camera and image sensor would be directly indicative of the presence of a camera or image sensor. And then we have related terms, which are more ambiguous, but are still related to the transducer in question. So we have video and resolution. These could refer to an image sensor, but at the same time, these could refer to video playback, a screen's resolution, things like this. So with that in mind, I want to talk about our primary algorithm called ranked key term set matching. This is a novel approach to match key terms within a corpus. So the way that this actually works, each transducer from the ontology has associated with it a term set that contains both indicative and related terms. Abstract device types that, again, were built from the ontology are represented by all the term sets for each transducer that is associated with that abstract device type. So, to give you an example, take the abstract device type of camera. We know that it typically has an image sensor and a microphone. The terms for image sensor could be camera, video resolution, etc., divided into their related and indicative terms. The same thing for microphone, and from there we can build a term set about that particular abstract device type. So this algorithm will estimate which abstract device type is most likely being described by the vendor materials that are provided as input. And once it selects which device type is the best candidate, it will match on the indicative terms to make a final decision on which transducers are present on the device. And again, once we've enumerated the transducers and made an estimate of which transducers are present on the device, we can directly map to the capabilities that those transducers have associated with them. We also have introduced some less strict alternatives, and by strict I mean in the sense of matching scope. So we also have unranked KTSM, which doesn't consider abstract device type, but only matches on indicative terms. And then we also have the unguided KTSM, which is the most naive, just raw keyword matching, uses the entire dictionary within the ontology, and will very greedily match against all of the different potential transducers. What's interesting is that this presents a trade-off. So on screen here we have on the left the enumeration accuracy for each algorithm, and then the incorrect transducer rate or false positive rate for each algorithm as well. And you can see that even though the unguided KTSM provides the highest enumeration accuracy, it also introduces the most error into the analysis. And so this presents that trade-off where, depending on what your solution or what you're applying our solution to, you may want to have a more stringent set of requirements for what you match on or not. Another interesting relationship that we presented in the paper is the proportion of term classes. So we have different vendor materials, each of which has a different proportion of indicative and related terms within them. And what we see is that depending on how the ontology is created, and depending on which documents have indicative and related terms, we can see sort of another interesting relationship where if you generally have a higher proportion of indicative terms, you'll generally have a higher enumeration accuracy overall with ranked key term set matching. At the same time, you'll see a downward trend if you have a higher proportion of related terms. So to wrap things up real quick, in summary, we've introduced the first approach to proactively extract IoT device capabilities from vendor materials to be leveraged in various security applications. We've also introduced a model to represent IoT devices, transducers, and their capabilities. We've introduced algorithms of varying matching scope to extract capability information from accessible vendor materials. And I'd like to mention that our code, our source code, and our repository is available at this link on screen now. And just a couple future directions to wrap things up. There's a couple of limitations that we'd like to address, including the manual review process. Part of this that we'd like to look at is the automatic discovery of ontology components like new terms, new associated transducers, this kind of thing. We'd also like to look at additional features apart from just text. We'd like to look at images that are on web pages, perhaps even the hierarchical layout of web pages that we were describing before. And then we'd also like to look into the extended capabilities of devices where you have what we might call composite capabilities where they're enabled by software, things like this. Additionally, we'd like to look at automatic refinement of term sets through some kind of machine learning-based feedback loop, for example. And then the application of MUD profiles in this work is a point of interest as well, where we could either automatically generate MUD profiles based on our technique or use or leverage MUD profiles that exist for devices in our ontology. Finally, we're interested in looking at deeper comparisons of vendors and their materials to see what kind of subtle differences in quantifying their terminology sets, their marketing techniques. And with that, I will say thank you guys for listening to my presentation, and here are some additional acknowledgments that we'd like to share. So yeah, thanks very much.